Okay, so hello everyone. My name is Mikołaj. As was said before, I am not primarily a firmware person or a hardware person. I work at Google on the confidential computing team. So primarily I work on virtualization security. However, a lot of the things related to confidential computing go through UEFI. So we do work with UEFI quite a bit, and we did work with a few different parts of the ecosystem. It's also my first time here, so I wasn't really sure what to expect and how should the presentations be prepared, so they're slightly different. The presentations, rather than expand what should we do or propose things, rather talk about some simpler parts of the UEFI ecosystem, how we manage to use it in a slightly different way than usually, and how it can be expanded. So the first thing I'd like to talk about is extending EDK2 functionalities to Gnu-EFI. So first of all, let's go through the agenda. So first I'll do a quick introduction of myself. I actually went through that already. Then we're going to talk very briefly about what Gnu-EFI actually is, our initial attempts of using it. Well, the attempts were somewhat failed. So we're also going to talk about how Gnu-EFI works underneath, because it turned out to be a necessity in actually using it. And then later, we're going to use all of that knowledge to simply talk about how would we be porting UEFI applications to it. So first of all, let's talk about what Gnu-EFI actually is. So building UEFI applications on Linux is rather problematic. So it uses a completely different build system. Windows natively builds PE32 applications or PE-COF applications. UEFI, which is what UEFI typically uses. GCC targets ELF binaries. Now, those binary formats are very different. However, the major problem when interacting with an application built in GCC and an application built natively for UEFI is the way they talk to each other. So the calling convention is rather different, and this will be a major point of this later on. So in order to fix this solution, there's this thing called Gnu-EFI. Gnu-EFI is hosted in SourceForge, and there isn't that much information about it. If one decides to scavenge the internet, usually what comes up is the repository itself and a very small article on OSDev wiki. And Gnu-EFI by itself is meant to be this magical sauce that will allow us to compile a native GCC application. We're going to link the Gnu-EFI libraries, and it's going to work out of the box on UEFI, or at least that's the theory that we've got to work with. So that's pretty much what happened. We've pulled Gnu-EFI. We've built an application that's meant to be used natively in GCC. Now, one other thing of why would anybody be caring about this? So it was mentioned before in the few talks before that there is a little bit of a pushback when trying to get GCC developers to actually work on UEFI. I think one of the talks before mentioned that people that got used to U-boot don't really want to go to UEFI. Now, if one ever decides to ask someone else to build a UEFI application, which is what we essentially did, it'll be the best for the developers to have the easiest time doing it. And it turns out that doing it with GCC is much simpler for them, rather than switching to the Windows stack. Additionally, Google, and I verified this before the talk, has a thing called nanolipsy, which is a framework that implements a very basic POSIX implementation that allows building applications to both Gnu-EFI and Linux. So whenever someone wants to have something that works in both ways, which is how we did a lot of our testing, one can use that system, which then in the end will trigger Gnu-EFI, which will build a UEFI application. Much simpler for a developer, much harder on us if anything doesn't work. And that was actually the case. So whenever Googling for Gnu-EFI, the thing that comes up first is the OSDev wiki. That doesn't have that much information, except it says pretty much what I said before. It says that it's simple, says that it's going to work out of the box, and that Gnu-EFI provides this magical wrapper that if you pass the function to it, you pass the amount of parameters, you pass the parameters, it's going to work out of the box. Well, that's what we did. So in our case, because we work on confidential computing, this is merely an example. It isn't that tied to the whole presentation, but it was our problem. We do have a function that's being used to clear the encryption in specific pages. The function isn't part of the UEFI API, so it isn't put through any of the runtime services or boot services. It, however, is in the code. So if someone natively builds an application, they can put it in the application folder, they can link it, it's going to work. So the first attempt after reading the wiki page, well, would be to simply call it with the UEFI wrapper. The UEFI wrapper is supposed to work, it's supposed to abstract it away. We pass the amount of the parameters. Well, as one can guess, it didn't work. It didn't work. There were no symbols for the function, it didn't compile, and well, that leaves us in a little bit of conundrum because we had to figure out how to actually get that functionality in there. And that got us into an adventure of trying to understand what Gnu-EFI does under the hood, how does it work, how does all of its magic work, and how can we extend it farther to allow other functions to be there. So there's three primary components of UEFI that I would at least be trying to implement if I were to be porting applications into my own ecosystem. First of all, we have the types. So UEFI has its own set of very large set of different types. So UEFI call functions return UEFI status. That's typically not existent in the standard libc implementation. Another thing is the functional calls. So previously we mentioned the function that we've been missing. UEFI has a lot of them that apps natively can use. One example would be allocating memory. UEFI gives us an allocator, so we do have allocate pool, allocate pages. All of those things are used by UEFI internally and visible to all the applications. And the third thing is UEFI API calls. And by UEFI API calls, I mean boot time and runtime services. Now everybody here probably knows everything about it, but in general, UEFI has an API that it gives to external applications to use. Services aren't really services, they're functions that other users of the ecosystem can do. The split between boot and runtime merely comes from the fact that some of those functionalities are no longer available after booting the system. So we did mention allocating memory that has a function before. There is also a boot service responsible for allocating memory. Why would it be a boot service? Because if someone started allocating memory while being already booted to an operating system, that would potentially cause a problem. Why is it a service and not merely a function? Well, we do want to maintain some sort of a state to keep all the stuff that's been allocated through all the applications of UEFI together. So first, let's talk about the types. And we did mention the EFI status type. We also, if we go back to our function, we do already see a few types that don't really exist anywhere else. So for instance, we have an input function called physical address. We have a return underscore status, an API. Those things need to make it into Gnu-EFI somehow. And I'll make an attempt at having this a little bit more interactive. What would be the easiest way of getting something into a new build system if we wanted to? Does anybody? So we could copy paste everything. And if we look at Gnu-EFI and the way it's done, and I did look for an example. This is from include EFI dev.h. And this file is very large, it just didn't fit on a slide, and I wanted to capture the most crucial parts of it. So we did mention physical address before. Well, it's a type def for UN64. We did mention virtual address. That's also a type def for UN64. And just to know that not everything here is a type def for UN64, although that's the most common case. We also have an enum for the allocated memory type. And that's pretty much the theme of everything here. So if anybody wanted ever to add a type to Gnu-EFI that they don't have access to natively, well, they're probably expected to copy it or create a library that Gnu-EFI will have access to that will read it. The other problem is the function calls. So we're not talking about boot and runtime services yet, which are part of the UEFI API, but simply standard functions like the one I mentioned before. Let's go again. Can anybody guess how that's being done?
EFI ECX, CBX versus EDI, ESI, right?
Sorry?
API. Yeah, API.
So, no.
That should be.
Oh, fair enough.
That seems pretty nice. They should have.
So the function, we're gonna go towards the translation of services later because that's part of the API. Right now I simply want to talk about things that are not part of UEFI's API. So not runtime services, but the function we called before. And those are copied entirely as well. Well, this is a minor example, the one I talked to before. And this is, well, allocating a pool of memory. It's located in lib.misc.c. And yeah, so the way this works is really simple. So far, it looks like a copy-paste of UEFI. There is, however, one major problem, and that's the APIs we've mentioned before, which is boot services, runtime services. Well, in order for an application to run, those need to be called. And the allocate pool is a good example because, as mentioned before, allocating memory requires going through a service. One could do it by themselves, but they're probably going to have to maintain a separate state. It's going to be inefficient and potentially very problematic once you boot into something eventually. So, as you can see, I hope this is visible, but one of the few lines in there actually simply calls the boot service. So that's what the UEFI call wrapper is for. The UEFI call wrapper is merely a way of abstracting away, calling all the APIs of UEFI. So now that we understand all of this, well, if we're porting a standard function that doesn't go through boot services or runtime services, we're probably going to have to make a library, copy it in there, link it against Gnu-EFI, and it will work. Not elegant, but that's the unfortunate reality. Now, if that thing has any calls to boot and runtime services, we're going to wrap it into this beautiful wrapper, and it's going to work as well. Not elegant, but the thing I wanted to talk about as well is the boot service and runtime service calls as well. Well, in an ideal scenario, this will work, but if we've managed to spend so much time on this, I'd like to talk about that as well. So they are not copied, as I mentioned before. And if we look back at the OSDev wiki page that I've mentioned previously, well, their examples also talk about boot and runtime services. So clearly this was intentional, this was the way it was meant. It was merely a misunderstanding on my part of what a function in the UEFI world actually is. But in order to understand it, I would like to track through the code, sort of follow through of what exactly does it that the UEFI call wrapper does. So we're going to talk about some of its uses. Well, first of all, let's talk very quickly about how boot services and runtime services are actually implemented, because it isn't entirely obvious. So it's not a service, as one might imagine. It's simply a memory location at a very specific point where there will be pointers towards those specific functions. So whenever we do have a runtime service, let's talk about boot service, we do have a boot service for allocating memory. We're going to have a very specific place in memory, that function is going to be located. Whenever anybody wants to call it, they will be able to simply do it. And well, Gnu-EFI uses that. So Gnu-EFI, rather than porting the boot services by themselves, which wouldn't necessarily work as the state is being maintained in UEFI, the boot services simply contain the references to the function pointers. And this is pretty much what this code snippet is about. So we do have a specific signature, the revision number of when this happened, and then there's a location. And underneath, you can actually see very specific pointers to boot services themselves. Well, this doesn't answer the question of how does Gnu-EFI make the conversion between ELF and PE32. So let's dig a little bit deeper into what the UEFI call wrapper does. Well, this isn't the prettiest define, but if we track it down, it takes the amount of function calls, it takes the function calls itself, it takes the name, and then slowly unwraps it into UEFI call 1, UEFI call 2, UEFI call 3, and so forth, till all of them get unwrapped together. So let's go further down and actually track UEFI call 3, which is the one which we're going to be caring about the most. So yes, this is the magic of how it's being done. Now I'm going to go slightly into everything that's being done here, as it contains a little bit of weirdness. It moves RDX to RDX and then comments it out, it allocates some memory. In the general way, it allocates some memory on the stack, moves a little bit of registers around, one of that's being commented out, then makes a call to RDI, and returns. So first of all, let's talk about the major differences when it comes to the calling convention between ELF and PE32. And I've actually made this just to capture the fact that the major difference is the registers at which the parameters are being called. So whenever we call, on the left side we can see PE32. On the right, we can see ELF. So the first parameter is going to be in RDI, second in RSI, third in RDX, and so on. While on the other hand, in ELF, we're going to have, on PE32, we're going to have them in RCX, RDX, R8, R9, and so on. All of them have a mapping. I think there's like 10 registers that are mapped to one another. However, when we go back to here, that's not necessarily what's being happened. So we're being told that RDI is mapped to RCX. Well, RDI is getting moved, it's getting called. RSI is getting moved to RDX. Actually, what we're moving towards RDX is, yes, is RDX itself. However, there's a reason, and it's tied to all of the fact that is happening here. So because we called this with the function pointer as the first parameter, RDI, which was supposed to store the first parameter, actually stores the pointer towards the function that we're meaning to execute, which is why we're calling it. That means that everything is slightly offsetted. So RSI will now be moved to RCX because the second parameter in our current Linux convention becomes the first parameter in our Windows convention, and so on. And then if we go back to the code, that is exactly what happens. This also puts us in a position where RDX gets moved to being itself. Well, it can be commented out as it's a null of itself. It's placed in there just to make it visual. One last thing though is the parameters are moved in a different direction than they are mentioned to avoid clobbering. And one might also be curious, why do we actually need to allocate 5 bytes on the stack? Well, that is implementation specific, and that is enforced by both ELF and PE32 if one reads the specs. Additionally, if we ever decide to call more parameters, because this goes up to 9 as far as I remember, we will be allocating more of the stack, and that is both also tied to how those implementations work. So yeah, now we know how the services are done. We also know how the UEFI calls, how the UEFI functions and UEFI parameters have been handled. So let's talk about what would we do if we actually encounter a situation where none of those are present. So first of all, as unfortunately mentioned, all the types and functions need to be moved there. Rather than copy-paste into Gnu-EFI, one can make a library, the library can be linked against Gnu-EFI, the files can be used, and that will work. It's not the most elegant solution, especially in situations where a function calls a function, calls a function, calls a service, which is very common in UEFI, and those whole chains are not being ported, but it's a sad necessity. The other thing is the boot and runtime services. As long as we use the UEFI call wrapper, those will work out of the box. The only problem is, for instance, a new service has been added to UEFI, or something has been moved around, although I don't think things get moved around in the structure, but linking a service that has not been there before and has been added now will require making an entry in that table. And that's it. That's how Gnu-EFI works on a high level, that's how we would be using it. Yes?
So I'm going to make a couple of statements. If you look at the EDK2 for quite a bit of time is built using GCC. If you look under base tools, source C, you can see this GenFW tool, and what you'll see in there is an ELF to PE call converter. So in practice, you don't need a specialized toolchain to build. So effectively, the way how EDK2 or binaries are built, if you're not using a Microsoft compiler, is very soon at Gnu-EFI, right? You build something as an ELF binary. Now, of course, you do pick your compile options carefully, but they're not like crazy. And then there's a conversion tool that spits out a PE conf. And this happens for every single architecture that EDK2 supports. So that's kind of one statement. Another statement is the GCC compiler, and I'm pretty sure C-Lang as well, lets you annotate a function API, which means this voodoo dance of put parameter here, put parameter there is archaic. You don't need to do it. All you need to do is do attribute, MSADI, and you're guaranteed that this function pointer will be invoked with the correct API. What does that mean? I'm not asking you to use time to core EDK2 as a build system. What naturally follows from this is, yes, you can create your own environment, that you can write your own applications. You don't have to use any of Time Core except for one thing, the headers. So if you look at MD package/include, which is effectively all you actually care about, it's only UEFI spec bits, and you can more selectively delete things which are not UEFI but are part of the PI spec or part of the Time Core implementation itself. You can end up with an extremely lightweight, make-file-driven environment that will go and spit things out for you. Has this been done? Yes, it has. And this is one of the interesting things, right? When you go work at a company and do something, right? You never really think about others. Like, wouldn't it be great if others actually knew about this one thing we had? And so I used to work at VMware, and it just turns out that they have such a thing. It's called ESX-Boot. If you Google ESX-Boot, you'll find it on GitHub. It's a GPL licensed bootloader, which is used by the ESXi operating system. And effectively, taking a look back, it's an entire environment writing boot applications that either work on legacy BIOS applications by using syslinux, or under UEFI, under x64, AIR64, or RISC-V. And they do exactly what I said. They just take in the MD package headers, as is, and then they have the L2P converter tool, which I believe has actually been adapted from the Gnu-EFI. And it's much easier. You don't have to do all this wrapper stuff. And then, of course, if you ever want to move your research out to like an architecture, you're going to have to sit there and wonder, like, so you need to worry about the difference between the EFI API and like the Linux API. So just go.
No, that's great to know. Gnu-EFI was sort of put out on us as a necessity at the time, so we were having to fight it, and this describes the journey of fighting it, but yeah, if we were to start from scratch, that's probably something we would take a look at, so thank you.
Yeah, so I was going to point out, Gnu-EFI was really important 10 years ago before the GCC compiler supported the pragmas for generating the correct API in the compiler, but it's not quite as important anymore now that that works. Mostly what he said, but the other thing to keep in mind is a relatively recent development since like 2021 is the Clang linker LLD supports generating or emitting PE32 natively, and it actually produces really good binaries, like better than the Visual C++ linker does, honestly. So, with that, you can do a much more, not quite a specialized tool chain, much easier now than you could have done like 10 years ago.
Say comments from me, really good to know. I'll ask this if we ever need to create ELF binaries that work in UEFI, that'll probably be the approach we'll try to go for.
Yeah, I mean, at this point, there's no real reason to start with ELF because the linker just produces PE anyway.
I have a funny story that relates to this. I also didn't know that the EFI API annotations of the functions is required because when you build with GCC, that actually decodes into the attributes that gives you the correct calling convention. And if you write yourself a debug library that does lots of printing all around the place and you forget to add that, you get the most hilarious errors when this actually prints out text. And it's ever so slightly garbled that you can figure out you can figure out that you're getting some information out, but trying to figure out what the hell is going on with your text. And it's just the calling convention, the registers are in the wrong place.
But I would suggest taking the MD package headers, not because there's a special place in your heart for Tino, but simply because those are guaranteed to be up to date. You don't have to ever ask yourself, do I need to figure out where this protocol definition? And the protocols are the other thing is you want to use in your case, the UEFI wrappers on them. You probably get pretty sick of copy pasting things in and out, right? I'll do the MD package headers.
All right, go ahead and move on to your next one.
I'll move on.